Okay, welcome everybody to our course. This is a case study on a Revit app we built that focuses on the title there, auto-generating and optimizing modular air duct layouts in Revit. Let's dive into it. So here's a little list of what we're going to cover today. Start by going over the team, the players involved, and then we're going to outline the problem we're trying to solve with this application. And then we'll show you the solution, the application we built. And then we're going to dive into a couple of the features that we think are pretty cool about this. Simulated annealing, you'll know what that is by the end of this talk for sure. User adoption, how we tried to achieve that, why it's important. And then at the end, we'll take a little step to go beyond air ducts to sort of show how the ideas we talked about in this talk, in this application, could be applied to like a whole host of things in the AEC world. Okay, let's get to it. So the team, these are the people and companies that were involved. I will start with myself. My name's Daniel Kay. I'm a classically educated architect, I guess. Got a 5-year Bachelor of Architecture from Syracuse, but also a minor in computer science, which kind of played into where I am now. So I've been working for like 7 years. I slowly kind of transitioned from architect to BIM manager, and now I'm at EvolveLAB. The last more than 2 years, I've been doing software development mostly. I'm interested in lots of the geometric spatial algorithms, really. It's my favorite stuff. Oh, and I am our official director of memes. It's on our company website. And then I'm here with Ben today. Ben, I'll let you introduce yourself.
Yeah, for sure. Thank you. Thank you, Daniel. So yeah, Ben Guler, partner and CTO at EvolveLAB. My background similar to Daniel's is in architecture. I went to school for that. Slowly transitioned to a BIM manager and then learned how to code. So then as soon as I did that, that was kind of my new passion and really wanted to do that full time. EvolveLAB opportunity presented. And so I kind of jumped on that trail and have been on that ever since. I really I'm a liaison here at EvolveLAB where I kind of help out with solutions for our clients and customers to our kind of dev team. So I also get to code myself, which is really fun. And I also have a wife and 2 daughters, which I enjoy taking hikes with. So it's really great. But yeah, that's me. For the next slide, I think we're going to just briefly talk about EvolveLAB. So EvolveLAB is made up of a diverse, eclectic group of individuals. We've got people with backgrounds in architecture, licensed architects. We've got people with computer science backgrounds, physics backgrounds, construction backgrounds. It's a really cool team that we've got here. And essentially, we help architects, engineers, and construction professionals implement design technology throughout the AC space. So that's us.
Yeah. I can talk about Henderson a little bit. Ben, you can hear me, right?
Yep.
Okay. Well, this is the engineering firm we work with. They also have like Henderson Building Solutions as a whole separate, but it's a really big company, kind of spread across the US. And these are we're highlighting some of the people we work closest with there, but it was a great team at Henderson. Yeah. Now let's jump into like the reason this partnership, why they reached out to us in the first place, which I would call the problem. Why can't the contractor just work it out? Which is, joke, of course. But it kind of summarizes what we're getting at here. Okay, so a little background first. Henderson developed this modularized duct system. There's actually an Autodesk University paper on it, a white paper by Adam Roth and Sean Turner, which I'd recommend checking out if you haven't read it. But basically, they developed the system with US engineering innovations for, you see pictured some of these modular duct parts and stuff. And there's a whole host of benefits to this, which they could go on about, streamlining the manufacturing and assembly process and design, all these sustainability aspects. But when we got together, the real crux was how do we get people in Revit designing using this kit of parts? So I'm going to go through just kind of the setting for this application. So what we have here on the left is a simple setup, very well-defined problem. There's a VAV box and then a branch duct, which is kind of already created, a little MEP system, if you will. And then air terminal layout that's also predefined. And what we're trying to do is get to the result on the right, which is to take that branch duct and break it into these modular pieces that they've developed, and then connect each of the air terminals to one duct module. And that's also made out of all these modular parts that are part of this big system. And then defining the problem like this for us to make this application really kind of simplified and helped us get towards success. I don't know, Ben has like I think this year, another talk at AU that sort of focuses on that. If you can find it at autodeskuniversity.com or wherever wherever this talk is. Yeah, Ben?
Yep, yeah, we've got another one which is going to be focused more on co-authoring, but yeah, this is kind of that case study on how we were able to kind of help out Henderson here.
Right. So what Henderson did to start is, like, this is how they attacked this problem. Like, built all these parts in Revit, like families, mechanical systems, etc. And then they made a proof of concept with Dynamo, which is sort of what you're seeing in the top half here, the script, which Dynamo is a great prototyping tool for things like this. And they were running it through Revit GD to optimize it. Version 1 of our application actually literally translated their Dynamo script.
Yeah, that's right. We actually like literally took the Python code and transpiled it to C#, and that was kind of our first kind of iteration. There were some things already figured out that we used for our generative like loop, basically, to make the first iteration of the code.
But I mean, the big problem, this is a great tool for power users that they were working on. But the big problem here is, I think this is a quote from Ben, power users design tools for power users. And Henderson's real goal here was to get their whole mechanical team on board, have everybody using this, not just like the Dynamo geeks or whatever. So that became, I guess, the crux of our problem. So to summarize, Henderson developed this modular duct system, and they prototyped it with Dynamo and Revit GD, so we knew it worked, they knew it worked. The goal of this tool is to connect a VAV box to all the air terminals using this kit of parts, and really make a tool that has high user adoption, that people use, that people not just are willing, but really like want, enjoy using. At least, that's the goal. Do we do it? I think so.
That's right.
All right, so what do we do? We'll get right into it. This is the app. We called it the Mechanical Runout Duct Generator app. This is the case study, right? So this is the case we are studying, essentially, this application here. So what is it? It's a Revit add-in that generates optimized runout duct and sometimes branch duct layouts using this pre-made DfMA kit of parts inside Revit. It combines different aspects of generative design and human input. So you get like a co-authoring approach, if you will. Let the computer do what it's best at, let the people do what they're best at. There's lots of analysis, optimization, so you can sift through different solutions. And then when you find one you like, you hit that little bake to Revit button, and bam, it just makes a fully connected like Revit duct system.
It's always so rewarding to watch that, to see how it kind of like press a button and all this content that's there, you didn't have to model yourself just as like, they're properly connected.
Bam, ready.
Always fun to watch.
I know, I could watch this GIF all day, but we don't have all day. So anyway, you look at this, you're like, wow, that's pretty complicated, Dan. How could I possibly understand that? Well, it's not that complicated, but luckily for you, we made this little course, Modular Duct Generator App 101, a simple 6-step how-to for using your custom mechanical generative design application, because everybody has one of those, right? Anyway, the 6 steps are: you select a VAV box, a variable air volume box, and different options. You draw that main branch duct we've been seeing, and then you generate solutions. Pretty simple, right? Then you can examine those solutions and bake to Revit when you're all done. Basically a summary of that last GIF. And the last step is a little different, but you can try to auto-generate that branch duct portion too if you want. We'll get to that. All right, now we're going to dive into each of these to really see how this thing works. Select your VAV box. So everything's already zoned, so you pick a zone with a box. There's a bunch of display settings on the right, which you can customize. These 2 sliders, I think, are probably the most important settings on here. We're going to talk a bit more about them later. But the problems we're working with, these are multi-objective optimization, which means if you make if you improve one aspect of a design, it's likely that you made another aspect a little worse. So those sliders allow you to assign weights about what's more and less important with this particular duct branch you're making. And then down at the bottom, there's some simulated annealing settings, which we'll talk a bit more about later. Okay, step 2. So you got all your settings, got your VAV box. Now you just click. You click at each vertice and it draws the main duct, branch duct, starts making all the runouts. Notice how it's already splitting it up into modules. It's calculating the corners. It's using some sort of modular system. That's what it's supposed to do. Going at specific I I mean, I made this job. I'm not a mechanical engineer, so some of these are little funny routes, but it shows what the tool does, okay? So step 3, you generate your solutions. And as you may have noticed, as soon as you start drawing that branch duct, solutions start being generated. I mean, the longer you stay in one spot, like leave your mouse alone, the better that solution is going to get. And then you can also, there's a regenerate button. If you change some settings, you hit regen and it'll run it again on the current branch duct. So once you have some solutions, you can examine them. In that little bar graph thing, you can click between them to activate different ones. If you hover over them, it'll give you a little more detail about each one and what those numbers and bars represent, kind of like that. So you can adjust some of those design constraints we looked at earlier in settings and regenerate until you have solutions you really like. And one thing I think is cool about this, like those solutions right now in the GIF, the numbers are really close, right? But maybe the designer will look at them and say, well, this one is obviously better than this one because it has a corner piece that's near a column that would be really hard for the contractor to get in there and assemble or something like that. Which comes back to this co-authoring, working together, the computer and the designer, to get the best output. So right, bake to Revit. So everything this app has been doing, we've been looking at it in Plan. It's all in 3D, the drawing, the algorithm. So you just click that button in the corner, and then it bakes everything to Revit, fully connected. You could run analysis on these systems, whatever. And a little shout out to the Revit MEP API, which is a portion of the Revit API. If you're not familiar with it, it's really powerful and really agnostic the way they set up these connectors. You can do a whole bunch of stuff with MEP components in Revit using it. We took advantage of it for this project. Oh, and one more thing I want to add here. One of the best parts of this, like bake to Revit button, is it makes your designs less sacred, in my opinion. Right. What I mean by that is, if there's a change in the design and you're like, oh, I don't want to, adjust. I spent 2 weeks modeling that duct system. I don't want to. Now you can just delete, do another design, rebake. Like you could bake 7 of them before your morning coffee, Like that's the idea. It kind of takes out all the monotony. Lets you really focus on updating the design with ease, right? So we have an auto gen button in the bottom. When you click it, instead of you drawing that main path, it'll draw it for you. Now, this is still in beta. I mention it because this was only like 12 weeks of developer time on this project. But you can see if we continue going, this might be the next step, improving this algorithm that generates the branch for it. Or maybe we move on to other things, like we'd start adjusting the air terminal positions to better distribute the airflow and shorten other runout ducts, or the VAV, or create the zones, which air terminals are in with all this stuff. Like we could this is kind of a preview of how we could expand it to that. Right, so failure is part of the process, right? So I thought I'd share a few of these. Like this system, 4 air terminals, 1 VAV. You think 4 modules up the middle, and 4 would be, but it likes to add this double 90-degree kink. Why? I don't know. I should know. Like I coded most of it. We got this zigzaggy one, which, you wouldn't build that in real life. Too much air friction, right? But to its credit, I think the zigzagging is because it does make all the runout ducts like shorter because it's trying to get as close as possible to each one. But again, we'd have to add some metrics to deduct points for extra corners. And then sometimes, like this one, spaghetti. And yeah, I don't really know.
That's a silly one, that one. Yep.
That's a beta feature. Okay, so to recap, we built this Revit add-in where you select a VAV box and options, draw your main duct branch, and then generate solutions. Examine those solutions, pick the one you like, and bake it to Revit. And then if you're brave enough, you can hit that auto gen button, see what happens. Okay, so now that we know how it works, we're going to start diving into the good stuff, why it works, in my opinion. Some of the cooler aspects behind the scenes of this tool. Simulated annealing. This is chapter 4.
That's right. The brains behind the BIM.
Right. Now, a little warning. We're going to start getting a little technical here. So feel free to go, get a snack if you're less interested in this part. This is my favorite part. Anyway. Okay, so we'll start with generative design. This is like, a huge industry buzzword. I think Autodesk has some good definitions I threw in here, but I really like an iterative process from a computer's point of view. Because once you know what these algorithms are doing, that's really what's going on. So here's a diagram of the manual way. So on the left, we create our initial design. I know it's pencil and paper. It's like representative. You're doing this in CAD or Revit. I know. I don't know. Maybe some people still sketch duct layouts first. And then you iterate, you redline, you talk with people, change the design, update the model, and it's a cycle. You keep doing that until it's ready to build. Now take a look at the computational design way.
Some similarities there, it looks like.
Almost the same. All you got to do is you take everything and you put it inside a monitor icon. No, but really, the computer generates the initial design, and then instead of iterate, and it scores the design with some metrics, and then it mutates, which is it slightly changes the design, it scores it again. Is it getting better, worse? What should I do? And then you build it when you have a solution you like. Right, what was I going to say? So you might ask, like, why can't I just generate every possible solution and then pick the highest score, right? And we're going to jump in the computer science world for a second, look at something called the traveling salesperson problem. I don't know. Ben, had you heard of this before we started this project?
Yeah, I think I've heard of it before for a different kind of optimization thing that we're building. But yeah, it's definitely learned about in the past 2 years or something like that. Like, oh, we should kind of get into this thing and kind of try to solve it.
I'm going to use it to help explain. And the idea is you have a whole bunch of cities and you have a salesman who has to get to all of them. And you want to find the shortest path. And believe it or not, we don't have a way for computers to definitively solve this problem. Here's a good example. Like an Amazon Prime delivery truck has to visit 60 addresses in one afternoon. What's the best order, to get my Amazon optimization? So if you look at this problem, with 6 cities, there's already 720 possibilities, which takes this really slow solver 11 seconds to try them all. If you add just 2 more variables, 8 cities, now there's 40,000. It's a lot more. Anyway, this solver, it would take 11 minutes. Went from 12 seconds to 11 minutes just by adding 2 variables. So imagine like 50.
It's a fancy word there. It's a pretty big number, looks like.
30.4 vigintillion. I looked that up. This is how many years at the same speed it would take to try all those possibilities. Of course, computers can go a little faster, but not that much faster. So if our computers can't try every solution, how do we solve like almost impossible problems like this? That's where we get into the field of metaheuristics. I feel really smart when I say this because it's like a big word. But if we break it down, it's pretty easy to understand. Okay, 2 parts, metaheuristics. I'm gonna look at heuristics first. Essentially, how this was explained to me, it's like educated guessing. It's when you have a problem that we don't know the answer to, and we don't know how to, we don't know how to figure out the answer. Like it's too complicated, too time consuming, or impossible to actually solve it. We just use guessing. And this is used in all sorts of fields. The chess engines use a version of this. Okay, and meta. Everybody knows what meta is. Not this one.
Not sure about that one.
This meta means like overall. I think it's a Greek prefix. Looking at from a higher perspective, that's good. It's also a common slang word these days. That's so meta. That's why I have the Urban Dictionary definition.
The meta game.
Right. So here's the chart. This is a nice graphic. There's a whole bunch of metaheuristic algorithms. A computer's best guess is a really good way to summarize it. A lot of these are nature inspired. Now the Revit generative design solver uses a genetic algorithm. So we're going to look at those first to sort of explain, I guess, the starting point. You may have heard of these before, so I'm going to try to go through this a little quickly. What is a genetic algorithm? It's inspired by evolution. It's also a little slow, just like evolution. So basically, you have a generation, and they make a bunch of offspring, I'll call them, and then you take the best of those offspring, and you make more generations. Like here, we have the scores, 2 offspring, and we're trying to go from regular people to really cool construction workers with badass glasses. So I made a few more, and then, first generation, you pick the best, 1 or 2 or however many. Like we got some cool construction hats here, good PPE. And you do it again. Notice the scores in general are going up, right? you can have as many children, as many generations as you want. It just, takes time. But eventually you can get to a really high level of mostly high scored solutions, some really cool looking, you got like the mono lens glasses. That's what you want, right? And you could do the exact same thing with mechanical duct layouts, which is why we're here, right? I just changed the icons again. By the way, all these icons, diagrams, I made with Autodesk provided icons for these presentations, which I'm pretty proud of. Moving on. So same exact thing with ducts. You could score them in different ways. And yeah. So if we hop back to the traveling salesperson real fast, you'll see on the left, we're trying all possibilities. And on the right, we're using a genetic algorithm. All of that gray mesh, it's generating like 60 ideas a second and then picking the best one. And you can see how much faster already. The one on the right, like that solution is already much better than whatever's going on the left. The important part, this is the exact same number of guesses. The one on the right is just, it's making better guesses, the genetic algorithm. That's what's called heuristics, smart guessing. Now, we already mentioned genetics can be kind of slow. Another con is they get stuck in local maxima and minima. What does that mean? I'm going to try to explain. So say you have an idea, right? Or a generation, parent, generate a bunch of offspring, you pick the best one, rinse and repeat, generate offspring, pick the best one, etc. You can see that they're sort of gathering near this higher score, but since the gene pool gets smaller, so the variation is smaller, so they all kind of end up clustering, and you think this is your best one, but actually this is what's called a local maxima. We don't know this, but there's a global max somewhere else that we just haven't found. That's really what we want to get to.
And the reason for that too, Daniel, is because you don't. Yeah. From one, you don't go lower. You want to go better. You don't want to go
right.
So right,
which is the hard part, right? You get what I call the idiocracy effect. If you haven't seen this movie, it's worth a hoot. It's worth checking out. Good piece of social, I don't know what you call it. Okay, so that brings us to this diagram again, where we have another algorithm called simulated annealing. Now this one avoids those local minima and maxima a lot better. It's also nature inspired, but it's inspired by the annealing of metal, which is where you heat and cool metal to make it stronger. It's very customizable, so this is how annealing works in a really broad sense. You take a metal, imagine these Tetris pieces are like the molecules, right? And you apply heat to it, and the molecules start moving around real fast, and then when they slowly cool, they form into like a stronger, I'll say better arrangement. That's annealing. So what is simulated annealing? It's an algorithm where we actually have something called temperature in the algorithm. It starts pretty high and then it slowly decreases based on the function. And the higher the temperature, the more likely we are to accept bad solutions. You'll see what I mean in a sec. That acceptance probability is the probability of accepting a bad solution, a worse solution than you already have. So if we take this graph and invert it, so the left side is the score now, not the temperature. We sort of have a range of acceptable scores. So as time goes on, the score has to be better for it to be accepted. So with this algorithm, we don't create generations all at once. We take one idea and we mutate it. We just continue to mutate it into either like this red one, it'll become unacceptably bad, and then we, get rid of it. Or, the algorithm will just mute until it has our better or best solution. As long as it's still above the acceptable range, we can keep rolling with it. The key point being, if you look at that blue line, your solution often has to get worse before it gets better, which is something genetic, just when you just keep picking the best, doesn't do as well at. Like the blue one. I mean, the red one, you can see that 71 is sort of a local maximum, right? Like we're not going to get anything better out of that, even if we keep iterating off of it. Whereas when the 40, it went all the way down to 13, that blue one, but from 13, we're able to change it into something really good. Like that quote, how's it go? Like you couldn't have invented the car by iterating on the horse. You got to take a step back to sort of change it even more. So here's that same graph. We're going to talk about the local minima and maxima, kind of follow a case study. So imagine now we're simulated annealing. So we're not generating, what do they call it? Not generating offspring. We're just iterating an idea on an idea. And as that temperature on the left stays high, it allows us to keep making, so like 3 is a lot worse than 2. But since we have a high temperature, we can keep playing with 3, Now it becomes even worse, but the temperature's still pretty high, so it's still okay. We're still playing around. Now you always know where all your previous best solutions are. So like 5 is the best one we've had yet, but we could always go back to one of our previous best and iterate on it. Like, oh, can 2 get better? Well, it didn't get better. Okay, let's go back to 5. Can 5 get better? Oh, look, it did. So, and as the temperature, now it's getting a little lower, like it'll start clustering around the best solution. So it'll iterate most around 7 and 8 and 9. So the lower the temp near the end, it tries to only refine the best solution. And then we get to the global max, ideally. And remember, like in the solution space, this line I have of possible solutions, that doesn't exist. You're just guessing. You don't know what solution's the best, just guessing in space. So we're building that graph. But remember, because of the traveling sales, we can't possibly calculate them all. Yeah, that makes sense?
Yeah, that would be the equivalent of like us knowing the graph would be the equivalent of us running the brute force one where it actually looks at every single possible one. Right. It's invisible. So it's really cool that you're showing that how that's just, we don't know it. We're running this blind, and from the points we extrapolate decisions to go this way or this way.
Right. So on the left image, it's not so important. It's the traveling salesperson in 3D being solved by simulated annealing. Check out that one on the right. When the temperature is low, that red line is all over the place. It's really exploring the solution space. The lower the temp gets, the more the red line stays near the peaks. And as it gets really low, you can see it really focuses in on that one peak in the middle because it figured out that's the max. That's the benefit of simulated annealing here. Okay. Sorry, skipped this. Anyway, so if you look at it right here, back to the traveling sales problem, last time, I promise, on the right we have simulated annealing. And that red line is the solution we're playing with. It's not the best one. The best one is black. The red is different. We're like getting worse to see if we can take that worst one and find a better one. And as time goes on, the temperature is dropping. The red will start to disappear. You'll see less and less red because the red and black are almost always the same near the end. It's like, low temperature, it narrows that red line movement, essentially. Hope that makes sense. But right, we're not here to talk about traveling salespeople. We're here to talk about ducts. So let's bring it back to the ducts. This is the exact algorithm we're using. Well, the base of the algorithm we're using to generate these things. That's what's going on. So we're only drawing the black, the best solution. We're not showing all the light gray attempts or the red one that's in the, it's only the best. But hopefully some of these settings will start to make more sense. I mean, it's a quick way to get really good solutions, really good guesses, essentially. It might not be the absolute best, but it's pretty good in hardly any time. Right, so we have settings, like one of those is simulated annealing start temperature, end temperature. Now you know what these temperature things are talking about. You can play with these numbers to kind of let it try for as short or long as you want. Like I said, it's a very flexible algorithm. And we have the results, like you can see how many solutions have been tried and improved. And I think when this runs, it'll give you 2,300 solutions. I mean, there's like vigintillions, right? And it found a good solution with only 2,300 guesses, which is like impressive, I think. Maybe I'm just a geek. I don't know.
It's very impressive, I think.
Right? Okay, recap. So we talked about what generative design is. In this context, we made everybody here sick of the traveling salesperson problem, maybe. And we gave you a word you can impress your friends with, metaheuristics. We looked at this evolutionary inspired algorithm, the genetic algorithm, and then some of the flaws with it, like how it's slow, can be slow, the local minima and maxima problem. And then we dove into simulated annealing, which is what's going on here, and the pros and cons of that. So now that we know how like the foundation of this, the GD in this application works, we're going to talk about how we got people to use it. Because really, like, if you build all this technology, but like people don't like or aren't adopting it, what was the point, right? I'm going to let Ben take over some of that. He's the expert.
Definitely. Thank you for that, Daniel. So let's see here. Right. So we'll start with, so basically, without adoption, the tool is just expensive marketing material. And we had to make certain considerations so that we really foster adoption. And then we build and design a tool that's not just for the power users that are very comfortable with minimal UIs and just even a command line UI, but it's actually, intuitive and easy to use for designers. So we started with integrating this directly within Revit. So any learned behavior of navigating through Revit, controls, things like that you don't have to learn that again. It's right within Revit. It's not a different software. It uses Revit native elements. So as you can see in this animation here, as you move those air terminals, if you hit regen, the connections go back to those new locations, basically. So it really works off of the native content, and it produces that native content. And this really starts to enable a co-authoring approach to the solution. So in order to enable co-authoring, we had to make certain app architecture trade-offs. And here's some of them that we had to do. One of them is interactivity over speed. So we'd rather want to feel like the application's never frozen, always kind of responses and displaying to the screen what's happening, versus kind of waiting a second and then when it's done, that's when you see the result. Speed over accuracy. So this really played a hand in our choice in the generic solver or the Metaheuristics solver, where we needed something that's really fast right away and has a decent result that's pretty good. So we really, at the cost of not using the perfect algorithm that does the best of the best, because we wanted that interactivity to be there. We wanted the user to co-author with the tool so that in case there's any changes that needed to be brought, let's say the solution's only 80% there, the user could fill that gap and fix that. Simplicity over customability. So as you can see in the UI, like we don't have most of these settings that are kind of under the hood that are a bit more elaborate are hidden away. Those are just kind of stored in the JSON file somewhere where we don't have to expose all of that. All that's kind of like baked into that. And another trade-off we did is specific over general. And shout out to the Henderson team for this one. They really made the problem modular for us, where it's just no pun intended, it's just a VAP box to the air terminals. It's not doing all the way from the RTU to even placing the air terminals. So the problem itself is encapsulated. And if you think of it as a module, you could have that module, you can have another module for just placing the air terminals like you've talked about earlier, Daniel. Like we could really modularize the problem, and then together they could connect and kind of grow into something a bit even more comprehensive that we already have here. Another consideration that we've made, and here I'm going to go to my next slide here, is obviously we have to pay good attention to the UI design. And so this is very important for user adoption. If I go next here, right. So many of you have probably seen this tool and have probably even used it to rename PDFs. It's pretty cumbersome and intimidating to use, but very powerful. So obviously not like this. We don't want to kind of have something that is intimidating to use, but we want to foster and kind of have that intuitive layout. So what we went with is a vertical design here where everything is scrollable. And at the top, we have the inputs. In the middle parts, we have all the settings and adjustments where you could adjust your constraints. We have a simple design options graph where you could switch through the design options at the bottom. And then at the very bottom, we have kind of this static bar that has your action buttons like drawing and baking to Revit. The other side to the coin for UI is UX, user experience. And what we have on the screen here is kind of displaying how our lightweight geometry is streamed to Revit, where when we turn off the ortho mode, because that one might make it seem a bit more choppy, you could see really how smooth the geometry is being rendered to the screen so that the user could at any instance kind of really, if you move the cursor a little bit, you could really visualize that and start to make decisions as it's computing on the fly live, essentially. Another portion that enables us to do is you could see the work in progress. So when the GD solver runs, right away it has an iteration, an idea of how things get connected, but it's not finished. It's kind of constantly thinking. And as soon as you change your inputs and you move your cursor, it's thinking more and restarting that because it has new inputs. So you always see kind of the work in progress of what the solver is doing as you are moving your cursor, clicking away through your design. Another thing that we really had to pay attention to and really enable this co-authoring workflow and essentially enable fostering adoption is the output. So the output is workable output. It generates native content. The modules, the families, everything is interconnected properly such that once you bake the solution, you could still make minor adjustments if that solution is not exactly what you needed it to be. And that kind of gives the designer a bit of a comfort and trust and ability to have a fallback in case something is not exactly the way they wanted to model it for that condition. And the last thing that I'll touch on here is make it fun. So it's really rewarding to use the tool to kind of have it animated and interactive and see this geometry being rendered to the screen. And it really feels good to generate all this content and just press bake, as we've seen earlier. It's just all this native content is there. And then you think about it, I didn't have to actually model that myself, and I could edit it and it's there for the project. So it's really great. So to recap, essentially, is these are some of the considerations that we had to make and really kind of drive to foster adoption. Is integrated within Revit so that you don't have to relearn new behaviors, new software. The app architecture trade-offs, where we had to have certain values over other values, intuitive UI UX design, workable output so that the user has a comfort for a fallback method, if anything, and then make it fun so that, it's enjoyable to use the tool, and make it so that other people could see, hey, you can show off the tool, like, hey, look, I'm working on this thing, and someone else could see it like, oh, this is fun. I want to try that tool. So just trying it is really fun to use. So
yeah, it is fun. I think it is fun. I think other UI and UX designers we've had, a lot of fun. I hope the Henderson engineers enjoy using it.
Yeah, and one thing I was going to mention too is, these are kind of things that we've learned on this project together and kind of utilizing this technology. But obviously, we could go way beyond ducts, and even within the ducts, as you've already mentioned, Daniel, even there's kind of space to grow there. And maybe you could talk more about that.
Right. I'm hoping by the end you can sort of see this technology. We applied it to ducts, but a lot of the lessons learned, technologies we've found out or developed, etc., we could use them for so many things. We're going to show you a few examples. This is not just ducts, this presentation. It's like so many things in or even outside the AEC industry. So one example, we made this schematic plan generator for this large architectural client. And what it does is creates interactive scored schematic floor plans. And it uses a physics-based metaheuristic generative design algorithm, which we know what most of those words mean, right? It's really cool. It employs similar co-authoring techniques. It's on a different platform, but it still communicates with Revit. It's still multi-objective optimization. This one has like 30 sliders, right? The Henderson, since it was such a box problem, I think it had 2 or 3, depending on which build you're looking at. I give a whole talk on some of these algorithms. And then we have Morphus. This is one that I think Ben is giving, again, another AU talk this year about, right?
Yeah, definitely. And just a little bit on this one, basically, it's using the same kind of ideas and concepts that we talked about in this case study and applying it to layouts. And then on the screen right now, we have just a kind of proof of concept of like an office where you're just kind of dealing with low resolution volumes that are mapped to families. And then you could just kind of iterate through them and see kind of metrics on, what your ratios are. And then you can even see how if you move a wall, it's kind of responding to that. And if you, draw, it's kind of actively kind of tracing your cursor. And when you're ready to kind of have something that's, somewhat acceptable, you could just hit bake, and then similar concept, you have all that content generated for you from the schematic geometry, within Revit as native Revit content.
Already in Revit, responsive, reactive, similar like UI techniques. Some other unique stuff in this one, but that's for a different talk. Anyway, and I started making a list, but really, in my mind, the possibilities are kind of endless. Like just with ducts, we talked about laying out the air terminals, or choosing what VAV boxes go with what zones, or maybe without modules, sizing the air ducts. But you could go into any discipline, like arranging, gravity drain pipes or sprinklers. That's a big one, I know. All these different construction applications. Some of these we actually have similar projects we've worked on. But all this and many more, I hope you guys watching this can imagine other ways to use these type of techniques, right? So in summary, coming to the end here, summarize what we looked at today, what we learned, I hope we learned. We looked at the problem, how to get Henderson's mechanical engineers using their modular system within Revit, and the app we built that was the solution to that problem. And then some cool aspects of it, like simulated annealing and different metaheuristic algorithms to sort of optimize in ways to, optimize speed and allow co-authoring. How to increase user adoption, lots of UI and UX design, and a whole host of other things that we've learned from trial and error and user testing. And then how hopefully some of these ideas from this presentation and technology could be taken beyond just modular duct layouts. These are really cool, I would say. But like to I mean, so many things that I'm sure we didn't even list. So I guess that's pretty much it. But if you have any questions, I personally could geek out over like any slide in this presentation for a few hours. So if you want to send me an email, I got this picture. Sorry, Ben, from our last our last company resort. You're in there. Some of our other teammates. Yeah. But again, any questions with this online presentation, feel free to reach out. Otherwise, I think that unless you have anything else, Ben, that is most of it for today's talk.
Yeah, thank you for joining us.